Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we go, folks, with another video. And of course, I am the Crazy Hat Chemist, and that's why you're watching this, because this is the best place to learn your chemistry. So today's video is the covalent bonding worksheet number 5. That's a Roman numeral 5. Hopefully you know your Roman numerals. Okay, before we get started with this video, I'm going to encourage you to do a couple of things. And that is, number one, you need a periodic table. And that periodic table, you need to know your valence electrons and you need to know your electronegativity comparisons of different elements. Your valence electrons are in columns. That's column or group one valence electron, column or group two valence electrons. And these are groups or families, really. Column, group, family, 3, 4, 5, 6, 7, and 8. Those are the valence electrons. And the most electronegative element, that is fluorine. Awesome. Fantastic. So you need to know that. Then further, what you need to know is you need to actually, prior to watching this video, you need to watch the covalent bonding worksheet number 1. You also need to watch covalent bonding worksheet number 2. You also need to watch covalent bonding worksheet number 3. And you need to watch covalent bonding worksheet number 4. That is all prior to watching this video. In addition to this, you also need to have this handout. And this handout is the covalent bonding handout number 2. It gives you the axe with the respective corresponding shape, molecular shape, and bond angle. In addition to that, before you actually have to do the axe, you need to be able to draw Lewis dot structures, and these are the rules for drawing Lewis dot structures. All right. And that's what you need. You actually need a model kit as well. So a model kit would comprise the following right there, folks. That's what you need. You need yourself a model kit because it's very essential that you have a model kit so that you can make these models. All right. So without further ado, let's peel these ones back. That's number 4. That's number 3. That's number 2. That's number 1. And there we go. We are on number 5. Okay. So here we go. So let's zoom on in here a little bit so we have everything that we need on this worksheet. And again, this is covalent bonding worksheet number 5. So here we go. Let's zoom on in. So you got everything here that's required for today's activity. You are not going to be getting a stamp here from me because this is just a YouTube video. But if you were in my class, you must build the model and show me everything before you get, quote, that stamp. All right, so here we go. Our formula for our first compound is C2H6. So you can look this up online if you want to, but this is the second simplest hydrocarbon. And so, yeah, that would be one of them. And this is ethane. This is ethane. All right, so what we're going to do is we are going to look up carbon on our periodic table. And for carbon, we need to find out how many carbon atoms there are. There are 2 carbon atoms. And we're going to multiply that by the number of valence electrons in carbon. And how many valence electrons in carbon? This is carbon, 4 valence electrons. So I'm going to multiply that by 4. That will be 8. Then hydrogens. There are 6 hydrogens. And how many valence electrons in each hydrogen? Each hydrogen has 1 valence electron. That's right. Okay, so it's 6 times 1, and that would be 6. We're going to sum these up. That's a total number of 14. And then what we're going to do is always divide by 2, and that's 7 pairs. So we're always working with pairs of electrons. That's the simplest. It's the fastest. All right, so here we go. We're going to have a carbon in the middle. So I'm going to do this off to the side here for just a moment on another sheet of paper, and you're going to find out why that this is correct or incorrect. So we're going to draw a carbon. And then what do we have? We have another carbon, and 6 hydrogens. So I had mentioned we're going to do X marks the spot, the sign of the cross, whatever works for you, plus sign. So we're going to have another carbon and then 6 additional hydrogens. So that's 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock. And then I have 2 more hydrogens to place here. So I'll just place them right here like this and right here like this. You're going to see, and hopefully you see this already, that you can only bond how many things to carbon? Carbon follows what's called the octet rule, and that's the octet rule right there. If you were to extend this and put another bond here on that hydrogen or another bond on that hydrogen, that would exceed the octet rule, and that is impossible for carbon. So what's going to have to happen on this molecule of ethane is that you're going to have actually 2 carbons adjacent to each other like such. Okay, and then you're going to spread the hydrogens around these, just like what you would normally do, kind of like in the X marks the spot pattern, sign of the cross, except we're going to go like this, and then here, and then here. Okay, perfect. And these carbons are somehow going to be attached together as well. All right, so our first hydrogen is in this 3 o'clock position. That's 1, and then another hydrogen in this other 6 o'clock, the alternate 6 o'clock position, the 9 o'clock position, and then we have 2 12 o'clock positions. All right, fantastic. Now what we're going to do is we're going to erase those pencil marks there because we're not going to have those up there. And now that's what we've got. We've got 7 pairs of electrons. So we're going to first place a pair of electrons between the 2 central carbons. Then we are going to start walking around our face of our clock, and that's 3 o'clock. That's for the second pair, third pair, and the 6 o'clock, and the other 6 o'clock, the fourth pair, the fifth pair in the 9 o'clock, and then 12 o'clock positions for the 6th and 7th pair. So we have 1, 2, 3, 4, 5, 6, and 7. We're going to verify the, excuse me, that's the duet rule. That's a duet. The duet rule for hydrogen. Hydrogen follows what's called the duet rule. The hydrogen follows the duet rule. Hydrogen follows the duet rule. Hydrogen follows the duet rule. Carbon follows the octet rule, and that's 2, 4, 6, 8. And carbon follows the octet rule, and that's 2, 4, 6, 8. That's fantastic. So that is perfect. I'm going to erase all that because that really doesn't belong. I actually do that inside my head, but I need to show that out to you so that it looks good. All right. Now, the next really issue that we have here is we're trying to look at this and figure out, well, what is the shape? And in order to get the shape, it's actually the shape is at each central atom. Okay, and so this is going to be carbon 1 because it's the first one, and then this is carbon 2 because it's the second one. We could have labeled these as carbon 2, then 1. It doesn't actually matter. However, now at each carbon, there's going to be a shape. And so what we're going to do is we're going to get the ax at each carbon. So the central carbon, we'll call it carbon 1. The central carbon for carbon 1 is the A. Then how many things are actually attached to this central carbon? Well, there's 1, 2, 3, and 4. So those are X's, and there are 4. There are no lone pairs on the central carbon. All right, now let's look at carbon 2. Carbon 2 has a central A, that is carbon 2. Attached to that physically are X's. This is X1, there's X2, there's X3, and there's X4. So you're getting actually the same axe-like structure for both of these. That's a good thing, by the way. We're going to look up AX4 on our chart here, and you should be having this chart. If you need this chart, by the way, then you're more than welcome to shoot me an email, and I will send it to you as a PDF. So this is AX4, that's tetrahedral. So I'm going to write tetrahedral. And then we got to get the bond angle, and the bond angle is right here with tetrahedral of 109.5. So 109.5 degrees for tetrahedral. Now we're going to build that molecule and then we are going to find out the molecular polarity. So here is that model right here. So you should see that right here is carbon 1, then carbon 2. And with carbon 1, there's a single bonded hydrogen, single bonded hydrogen, single bonded hydrogen, and then a single bonded carbon. With this carbon 2, there's a hydrogen, single bonded, hydrogen, single bonded, hydrogen, single bonded. You can look at it at this end as well. Just looking at it straight on through the carbons. And then we can turn it and twist it as well. So just so you've got that idea. So is this a symmetrical molecule? Yes, this molecule is symmetrical. Okay, so everything's the same on the outside effectively. I'm touching everything the same on the outside. So because it's symmetrical, that means it is non-polar. Fantastic. There we go. That is with ethane. That's a gas, by the way, in temperature and pressure. And yes, they would be alternating here like this instead of like that. That would be what's called steric hindrance. And maybe when you get to your organic chemistry class, that would be a steric hindrance. That means that these atoms kind of are bumping into each other. And that's why it's going to be more of this alternating pattern. And that way the atoms and the electrons around them require a little bit more space. It makes more difference when the atoms get bigger. All right, so let's put that off to the side. We're going to do the next one, which is C2H4, and that is ethene. Ethene. So how many carbons do I have in ethene? That's 2. How many valence electrons in carbon? Well, I need my periodic table for that. And carbon is right there. There are 4 valence electrons in carbon. So that's 4. So that's 2 times 4. That is 8. Hydrogens. How many hydrogens? There are 4 hydrogens. And how many valence electrons in a single hydrogen? That is 1. Okay, and so that's 1. So that's 4 times 1, that's 4. I'm going to add these up here, and that will be 12. I always divide by 2, and that will give me 6 pairs. Perfecto. Right, so we're going to do something similar that we did with the last one, and that shouldn't be a problem. Okay, so we're going to do something similar, like I said, to the last one, but we have the same problem, and that is we have 2 carbons. Okay, and then we're going to place some hydrogens around it. So a hydrogen here, and I'm going to just place the hydrogens around the carbons as far away as possible from each other, if you will. Okay, and so we'll call this carbon 1 and we'll call this carbon 2. We're going to place these 6 pairs of electrons. So we're going to do 1, 2, 3, 4, 5. So our first rule is to place bonding pairs of electrons between the central atom and the outside atoms. That we have done. Then the next rule is to place lone pairs on the outside atoms. And then if we did that even with one of the hydrogens, you should see that we have violated the duet rule for this hydrogen. The duet rule is already situated and obtained by having this single line here of this single bond. That's a pair of electrons. So if I put another lone pair on the outside of a hydrogen, that's always wrong. Why? Because well, that violates the duet rule for hydrogen, and that's impossible. So that means that we cannot place the electrons around the hydrogen, and that is the second rule of placing electrons. The third rule of placing electrons is to place them on the central atom. And you can choose either carbon 1 or carbon 2 for this job. All right, fantastic. So now what we're going to do is we are going to circle our atoms and count up the electrons. So that's a duet for that hydrogen, a duet for that hydrogen, a duet for this hydrogen, a duet for this hydrogen. And how many electrons around carbon number 2? That's 2, 4, 6, 8. That's good. That's an octet because carbon follows the octet rule. How many electrons around carbon 1? 2, 4, 6. Uh-oh, that's a problem. So You notice like in a previous video here, you should see that there's an intersection area right here between carbon 1 and carbon 2. And I need both of the carbon 1 and carbon 2 to have an octet. So what we're going to do is we're going to erase this pair of electrons and we're going to actually keep them with carbon 2 because carbon 2 already has an octet. But we are going to bring them in to carbon number 1. If you look at this intersection area, that means it's going to be with carbon 1 and with carbon 2. So I'm not removing them from carbon 2 and I'm not giving them solely to carbon 1. I am actually sharing them with carbon 1 and carbon 2, and that will be a double bond. So I'm going to erase this lone pair of electrons and I'm going to erase all these circles because that verifies and validates the octet rule for all of the 2 carbons there. And that's what you should see with that. That looks beautiful. Okay, and just like on the last problem, we're going to make an axe to get the geometric shape at each carbon, carbon 1 and carbon 2, which will be the same shape for both. The A is the central carbon, and that's either carbon 1 or carbon 2. The X are the elements that are physically attached to them with bonds. And so for carbon 1, that's 1, 2, and 3. And let's try carbon 2. Carbon 2 has an A, and then 1, 2, and then 3. So both of them give AX3. AX3 leads to what? AX3 is trigonal planar. So trigonal planar or trigonal planar, one or the other. And then that has a bond angle of 120 degrees. Okay, now what we need to do is build the model and then we can figure out what goes on from there. All right, notice that with the ethane structure of which we had previous, those carbons were singly bonded. Now with this ethene structure, then you should see that the carbons in the middle are double bonded. And you can see that right here. Hopefully you can see the difference between a single bond and a double bond. The double bond has the 2 of these, and 2 of these would be 2, and that's a double. This is a single, and that's a single, right? So you should see that the atoms of all the atoms are actually in the same plane. That is, the hydrogens and the carbons are all within the same plane. That's why it's a trigonal planar structure. And you should see that this here, right here, if we were to look at this and this right here, so this hydrogen, hydrogen, carbon, and carbon, they are all in the same plane, and that forms a trigonal or trigonal plane. Same with this carbon here has this hydrogen, hydrogen, carbon, and carbon all within the same plane, trigonal planar structure. So each one of these is trigonal planar. If I touch on the outside atoms, are they the same? They are the same. So that means that this is symmetrical. And if it's symmetrical, then of course it is non-polar. Cool. That's fantastic. That looks really good there. All right. All right, I'm going to point out something here, and we're going to go for the next one. We have ethane, ethene, and then this next one, C2H2, is ethyne. Ethyne. So ethane, ene. And this is also called acetylene. That's another name for this. This is a very, very flammable, colorless gas. And it's used in acetylene welding and torches. And it's a very, very fuel. It's a fuel, right? So we're going to get up the valence pairs of electrons for this. There are 2 carbons, and carbon has how many valence electrons? Yep, probably shouldn't have to pull this out anymore, but carbon has 4 valence electrons. So that's 2 times 4, that's 8. And then hydrogen, there are 2 hydrogens, and how many valence electrons in a hydrogen? That's a 1. So I'm going to multiply that by 1. It's 2. I'm going to add those up, and I'm going to get 10. And as always, I divide by 2, and that will give me 5 pairs. All right, fantastic. And just like before, we are going to set this up in a similar fashion as in the previous um, two, and that is that we are going to have a carbon one and another carbon one, sorry, carbon one and carbon two, apologies. And then we're going to place these hydrogens as far apart as possible on here. Excuse me. We're going to place a hydrogen here and another hydrogen there. And we have 5 pairs of electrons. So the first is placing bonding pairs of electrons between the central and outside. Okay, central and outside, that's 2 bonding pairs and 3 bonding pairs. The next rule is to place lone pairs on the outside atoms, of which I cannot do. So that's 1, 2, 3, 4, 5, because those are hydrogens. Hydrogen follows the duet rule, so that's impossible. So don't try to do that. So then the next rule, the third of the 3 sets of rules, is to place lone pairs on the central atom. And you can do this, separate them between carbon 1 and carbon 2, or you can put them all on carbon 1 or all on carbon 2. It doesn't actually matter. Okay. I'm going to circle this right-hand hydrogen in the 3 o'clock position, and that has a duet. This 9 o'clock hydrogen has a duet. This carbon 2 has an octet. That's 2, 4, 6, 8. This carbon 1 has 2, 4 electrons, so it is lacking electrons. So again, just like I'm going to shade this intersection right here of the 2 carbons, carbon 1 and carbon 2. Okay, that's where they're sharing electrons. So this pair of electrons, carbon 1 and carbon 2, are both sharing. Carbon 2 has an octet, carbon 1 does not. So I'm going to bring this pair of electrons into that sharing section, and that will give me a double bond right there as I erase these. That still maintains an octet that's 2, 4, 6, 8 on this carbon 2, and it increases the number of electrons in carbon 1 by 2 electrons. So that's 2, 4, 6. It had 4, now it has 6. I'm going to have to do the same thing since I need an octet for both carbon 1 and carbon 2. So I'm going to take this pair of electrons, bring them in, shade them out here, and then bring them into this sharing area here. And now you should see that carbon 2 still maintains 2, 4, 6, 8 electrons. And now carbon 1 has 8 electrons. That's 2, 4, 6, and 8. So I'm going to erase all those pencil marks that we just did there. And then you should see that structure for acetylene or ethyne. All right, fantastic. So, and then we have a structure here. We're going to have the axe-like structure, AXE. So our A can be carbon 1, and then our X are the physical atoms physically attached to that. So there's this hydrogen here and this carbon, that's AX2. Or we can look at the central atom as carbon 2, and that's an A, and then X1, X2, and that still gives me AX2. What does that give me in terms of a shape? AX2 is linear. Linear. And like you would think, linear would lead to a bond angle of 180 degrees. 180 degrees. Now we need to build the model. Here's the model. You should see that there is a triple bond here in between the 2 black carbons, and that has a triple bond there like that. That's perfect. Okay, and you should see that the atoms are linear to each other. On the outside, if I touch all the outside atoms, they are the same, and that is symmetrical. And then, of course, non-polar. Non-polar. I'm going to put up these 3 here that we have here. So this is the last one. That's the ethyne. Here's the ethene. And here is the ethane. So I got ethane, ethane, ethene, ethyne. Okay, single bond, double bond, triple bond. Okay, and before a quick little advertisement, I want you to see that the ane represents a single bond. Okay, the ene represents a double bond, and the Ine represents a triple bond. So this is a little pre-organic chemistry learning for you right now. So the ane represents a single bond, the ene represents a double bond, and the ine represents a triple bond. So I want you to look at the back of some kind of foods and stuff like that. I want you to find an ane, an ene, and an ine. And when you find those, you know that there is going to be a single bond, a double bond, or a triple bond in those formulas. All right, so what we need to do is move this worksheet up so we can do our last two. So I'm going to move this worksheet up here just a bit, okay? And so that we can do our last two problems. But before doing our last two problems, we need to give our sponsor of our video a little bit of advertisement here. So today's sponsor for today's video is, that's right, the Crazy Hat Chemist. So the Crazy Hat Chemist, that is me. I am sponsoring this video, and hopefully that's working for you. Whew, that's fantastic. All right, thank you very much. A word from our sponsor. And our sponsor is really excited to produce more videos just for you and your chemistry learning, because we are all about your chemistry learning. That's we, that's, well, actually, that's singular. That's just me. All right. So the next one here is boron trifluoride. So I'm going to highlight something here and underline it. That's tri, and the prefix for tri is a 3. And then we have fluorine. So that means there are 3 fluorines. So we have boron, that's boron. We have fluorine, that's fluorine. And then we have trifluorine. So that's 3 fluorines. Just like that. Really simple, actually. That's binary covalent compound nomenclature. So boron, there's one boron, and how many valence electrons in boron? You know, I mean, boron is the most exciting element on the periodic table. Of all the elements on the periodic table, boron is the most exciting one. And so that's why everybody likes boron, because it's so exciting, right? Boron, that was a little bit of chemistry joke here, humor for you. Hopefully you got that. Boron is right here. It has 3 valence electrons. All right, fantastic. So that's 3. So that's 1 times 3. That would be 3. Okay, and then fluorine, there are 3 fluorines here. And how many valence electrons in fluorine? Well, it's the most electronegative element. That's right there. And, well, there's 7 valence electrons in fluorine. So that's 7. And 3 times 7 is 21. I'm going to add up these two numbers, the 3 and the 21. I'm going to get 24. And like always, we divide by 2. And then we get 12 pair. Okay. Which element goes in the middle? It's either the boron or the fluorine. And it's the least electronegative element that goes in the middle. So there's boring. There's boron. Sorry, it's not boring. Oh my gosh. You got that joke, hopefully. That was on purpose. Or on porpoise, one or the other. So that is boron right there, and there is fluorine. So we're trying to find the element that is farthest from fluorine, but never hydrogen. Well, cannot be fluorine if I have another option, so it's going to be boron in the middle. So boron in the middle. Then we have X marks the spot, the sign of the cross, whatever works for you on that. There we go. I'm going to place the other elements in the 3 o'clock position, in the 6 o'clock position, and in the 9 o'clock position. I only have 3 of those fluorines, so now what we're going to do is erase those dashed dotted lines. Excellent, just like that. Now we need to place our 12 pairs of electrons. So the first rule is to place bonding pairs of electrons between the central atom, that's the boron, and the outside atoms, that's the fluorine. Central atom and outside atom, central atom, outside atom. I've used 3 of my 12 pairs, so I have 9 pair left. My next rule is to place lone pairs of electrons on the outside atom. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and finally 12 pair in total. Now what we're going to do is validate the octet and duet rule. There's no hydrogen, so I don't have to worry about the duet rule. So it's an fluorine right here in the 3 o'clock position has 2, 4, 6, 8. This fluorine right here in the 6 o'clock position has 2, 4, 6, 8. This fluorine right here in the 9 o'clock position has 2, 4, 6, 8. Now we're going to look at that central boron, and that will have 2, 4, 6 electrons. Well, that is less than an octet. So most times what we would do is we would have to move a pair of electrons from one of these fluorines into that boron to make a double bond. However, we need to make sure that we pay attention to all the rules on the sheet of paper that I have here. And so I've already highlighted this rule, but this rule I, it says boron and beryllium can be electron deficient. That is less than an octet, and this is acceptable. So, is boron less than an octet? Yes, it most certainly is. Is that okay? Yes. There's only two elements that can be less than an octet, and that is boron and beryllium. Those are the two that can follow that rule. Of course, hydrogen follows its own rule, and everything else is the octet rule. So I'm going to erase what we have here, and that is acceptable not to double bond a halogen. In fact, it's one of the most common errors of is to double bond a halogen. We'll discuss that in another video. So AXE, that's what we want to get. The A is the central boron, and the X's are the atoms that are physically attached to that. Those are the X's, and there's 1, 2, 3 X's. So I have AX3. I'm going to look on my sheet of paper, find AX3. And here we go. That is AX3. That is trigonal planar. Trigonal planar, and then AX3 trigonal planar is 120 degrees. So that's 120 degree bond angles. All right, now we're going to build the model and go from there. So here we go. One of the things that you need to make sure that you do, and that is when you are building these models, you need to absolutely make sure that you are looking at this handout that I have here with my model kit. So I've made this myself, and this corresponds to what's on the model kits themselves. Okay, I actually need a 3-hole here. It's a 3-hole tin. That's a 3-domain structure. There are 3 domains surrounding this. Okay, and that's why I have to use that tan one right there. This is trigonal planar. So, I mean, I always think, hey, look at that. That's super cool. All the atoms are within the same plane. All right, that's what we're looking at. If I touch all the outside atoms, are they the same or different? They're all the same. That is symmetrical. And symmetrical means nonpolar. Okay, fantastic. That is the trigonal planar structure, and I always like that one. I think that that is super cool, just like that. All right. Now what we're going to do is we are going to do our next one as soon as it stops spinning here around. I thought that that would be just kind of a fun thing. Quick little advertisement here from our sponsor, the Crazy Hat Chemist. That's me. Please like, subscribe, make a comment. The comment section, if you've noticed, it is out of control. The number of likes are just going exponentially growing. Okay, let's go for the next one here, and that is beryllium. That's a BE for beryllium. And then we have di, and that prefix di is the number 2, and then chloride. So that's Cl. So it's Cl and a 2. All right. So how many berylliums do you see here? There's one beryllium. And I'm going to look on my periodic table, and I'm going to find the number of valence electrons on beryllium. Beryllium is right here. That's a beryllium or beryllium, and that's 2 valence electrons. So that's 2. So 1 times 2 is 2. And then chlorine. Notice that I didn't put a C and then an I. This is not carbon and iodine. Nope. That's not correct. It's a chlorine. Okay. So how many chlorines? There are 2 chlorines. How many valence electrons in chlorine? Well, there's 7. It's in the same group family as fluorine. Everything in this same group or family has 7 valence electrons. So that's 7. So 7 times 2, or 2 times 7 is 14. I'm going to add these up. That gives me my magic number of 16. And as always, we work in pairs. That's 2, so that's 8 pairs. The least electronegative element goes in the middle, but never hydrogen. So between beryllium and chlorine, I'm going to find out where those are. So the least electronegative element is the one that's furthest from fluorine. So here's chlorine and here's beryllium. Well, it's hopefully obvious which one is farthest from fluorine of the two, chlorine or beryllium. Beryllium. So that means that beryllium goes in the middle. Okay? All right, beautiful. Now, the next one is to place these other atoms in the X marks the spot, sign of the cross, and that's the 3 o'clock position and the 6 o'clock position. Okay, erase that X marks the spot there like that. Beautiful. Okay, looking good. This is our last problem on this worksheet, so hang on in there. Don't go away. Stay tuned, folks. Stay tuned. All right, we're going to place our electrons, and our first set of rules is to place electrons between the central atom and the outside atom. Sounds central atom and the outside atom, and then the next rule is to place lone pairs of electrons on the outside atoms. So that's 1, 2, 3, 4, 5, 6, 7, and 8. 8 pairs. Okay, I'm going to verify the octet rule. That's 2, 4, 6, 8. The octet rule, 2, 4, 6, 8. The octet rule, 2, 4. Oops. Uh-oh. Wait. Hold on. Just wait for a second. Just wait time. Boron and beryllium can be electron deficient. That is less than an octet, and this is acceptable. This is beryllium. Is it less than an octet? Yes, it is. Is that acceptable? Oh, most certainly it is. Okay, so we're going to erase this, and this is okay. And another rule is you never double bond a halogen. Again, I'm going to make a separate video on that. We do need to come up with the X. Excellent. And that is the A for the beryllium. And then X's are the atoms that are physically attached to it. That's that chlorine, and that's a 2. And then we're going to come and look at our sheet of paper. That's our AX2. Whoops, upside down doesn't work. AX2 is linear. If it is linear, then it has a bond angle of 180 degrees. Now we need to build it. It will come. Here it is. There it is. That is the beryllium, and that is a chlorine. That's a chlorine. That's a single bond. That's a single bond. I'm not showing the lone pairs of electrons here on this model. So am I touching everything the same on the outside? Yes, I am. So that's symmetrical. And that is nonpolar. Fantastic. So that's symmetrical and nonpolar. I want to make a comment here on a couple of items here. This Lewis structure is correct. Could I draw another Lewis structure that is, and could I draw this? BeCl, Cl, line, and then the 3 sets of lone pairs of electrons. Could I draw this structure as well? Yes. Is this a valid Lewis dot structure for beryllium dichloride? Yes, it is. Does that show that it's linear? Yes. So I don't want you to think that just because you've drawn it, that is the shape. That shape is not a bent angle of 90 degrees or anything like that. And same with this trigonal planar structure. This is not 180 and that's 90. No, it's bond angles of 120. So this bond angle is 120, this bond angle is 120, this bond angle is 120. So you can have correct Lewis dot structures, but incorrect acceptance of it, if you will, in the Lewis dot structure, but the Lewis dot structure is most certainly correct. What we're going to do is we're going to zoom out of this worksheet here, and we're going to have a little note by our sponsor, as well as drawing and showing these molecular shapes. So here is the last one. That is selenium for beryllium dichloride. This is the second to last one, and that is the boron trifluoride. Then we have acetylene or ethine. then we have ethene, and then we have ethane. So that's all of them right there. Oh my gosh. I am the Crazy Hat Chemist, and this is the place that you come to learn real chemistry. I'm not giving you that fake garbage junk. This is actually real good chemistry. So this is the place to come. Please come back, like, subscribe, and I love you. Thank you very much. Bye for now.